Welcome to Shanti-Peace for mathematics. In my previous video, we have seen a method of separation of variable, and in that we have solved certain examples of partial differential equation and using the method of separation how to solve them. In the previous one of the video, we have solved a wave equation, that is a vibration of a string of a finite length using the D'Alembert solution. In this video, we are also solving a wave equation, but this is using a method of separation of variable. For that, we should understand what is one of the important concepts that is known as a principle of superposition. If you consider your general homogeneous partial differential equation of the second order in this manner, then if the u1, u2 up to un is a finite set of solutions of that partial differential equation in the region R, and if the series, that is summation of un, is convergent, not only it is convergent but the term by term differentiation is possible in that series, then by principle of superposition we say that the u, which is summation of un, is also a solution of equation 1. So basically, principle of superposition is tells you that if u1, u2 up to un is a solution and it is satisfying the certain condition, that means the infinite series which conversion, and not only it is conversion but it is term by term differentiation is also possible in that, then we can apply this principle of superposition and it tells you that the summation of that infinite series of un is also a solution of the given problem. So we'll use this principle of superposition to find out the solution of a wave equation using method of separation of variable. For that, let us consider a problem of vibration of a string of a finite length. That means we have a string which is attached with the two ends. A length of the string is we consider as L. So starting with x is equal to 0 is the, and this point is x is equal to L. And we'll fix that both the end with some, and we have already arrived at the governing equation of the motion of this vibration string is ytt is equal to c square yxx, and we are having the initial condition, that is initial displacement we are taking as f of x. That means at time t equal to 0 we are considering the displacement is f of x, and at time t equal to 0 we are considering the velocity is g of x. That means these two conditions are initial conditions, and we'll consider also some boundary conditions where at this end points, that means x is equal to 0 and x is equal to L, the displacement at any time is 0. So with this, considering this problem, we'll like to solve here this problem using the method of separation of variables. So for that, as we have discussed in my previous lecture, whenever we are applying the method of separation of variable, we assume that a solution is separated into two functions. Here the variables are given, it is t and x. So let us assume that the solution of equation 1 is, so we'll assume that this is the equation 1. This condition will say it is 2, this condition it is 3, and this condition will assume it is 4. So the solution of the equation 1 is y of xt equal to capital X of xt and t of t. Now we need to substitute this value of y into this equation 1. So for that I need to calculate what is ytt and what is yxx. So we note that yx is xt into t, because the derivative of this y with respect to x is x dash t, that is dx by dx into t, because this t is independent of x, so that we can do it, and yt is x into t dash, and yxx is x double dash into t, and ytt will be x into t double dash. Putting this value in equation 1, we obtain, so the equation 1 is this, ytt minus c square yxx is equal to 0. So that's why we have it as x into t double dash minus c square x double dash t equal to 0. Now this equation, if I divide both sides by x into t, so dividing both sides with x into t, we get x double dash upon x is equal to 1 by c square t double dash upon t, because you just see that if I divided this quantity by x into y and then we'll divide by c square, we'll have it is t double dash upon t into 1 upon c square, and this side is assume as lambda. Let us say this is lambda, and this, if I consider this will as a lambda, this will gives me two ordinary differential equation, that is x double dash minus lambda x is equal to 0, and the another equation will have t double dash. If I can multiply this square t on the other side, it is minus c square lambda t equal to 0. So we'll have two ordinary differential equation, and we have to solve this two ordinary differential equation using this initial as well as this boundary conditions. So first of all, let us try to use this boundary condition, that is y of 0t is equal to 0. So if I use that boundary condition here, from equation 4 we have y of 0t is equal to x of 0t into t of t, that is equal to 0 for every t greater than or equal to 0. But time function is not 0 because we are looking for non-zero solution, because a 0 is always a solution for this problem, because 0 is always satisfying this. But we are not looking at the zero solution, we are looking for non-zero solution. So we say that since t of t is non-zero, if t of t is 0, then we have a zero solution. That's why we are not considering 0 as a solution. We'll and have it as x of 0 is 0. And similarly, if I can have the another boundary condition, that is y of lt is 0. Similarly, y of lt is equal to x of l into t of t, and this is equal to 0 we have given, that is our boundary condition. And so that we can have x of l is 0 because t of t it is not equal to 0. So we have this. Now we'll start with the solving x double dash minus lambda x is equal to 0 with the two conditions, that is x of 0 is 0 and x of l is 0. This is the ordinary differential equation with these two conditions that we have. And we can say that this is actually the eigenvalue problem, which is an eigenvalue problem. And this lambda is actually called as eigenvalue of this differential equation. And there are three cases is possible depending on this lambda, whether this lambda is positive, whether this lambda is negative, and lambda is equal to 0. So we'll consider that three cases one by one. We'll have case number 1, that is lambda is greater than 0. If lambda is greater than 0, we'll take lambda is equal to b square for some b belongs to R. So therefore, we have x double dash minus b square x is equal to 0 because the value of lambda is b square. So this will gives me d square minus b square of x is equal to 0. So the auxiliary equation, this is the ordinary differential equation of second order. So the auxiliary equation is m square minus b square is equal to 0. That will gives me m square is equal to b square, where we know that this is b square is positive, so that's why this gives me m is equal to plus or minus b. Hence the solution is x of x is equal to a into e power bx plus b into e power minus bx. This will be the solution we can have because it has two distinct real roots. The auxiliary equation has two distinct real roots. Then this will be the solution where this a and b are arbitrary constants. They are arbitrary constants, and this x is should satisfies this boundary conditions that we have x of 0 is equal to 0 and x of l is equal to 0. That's why if I can use that boundary condition, now we have actually x of 0 is equal to 0. If I substitute x value here, that will gives me a plus b equal to 0. That will implies a is equal to minus b. And x of L is also 0. This will implies that a into e power bl plus b into e power minus bl is equal to 0. But the value of b is minus a, so that's why this will gives me a into e power bl minus a into e power minus bl equal to 0. If I take common out a, then this will return as e power bl in minus 1 upon e power bl is equal to 0. But this will gives me a into e power 2bl minus 1 upon e power bl equal to 0. But this will gives me a equal to 0 because this quantity, that is e power 2bl minus 1, is never equal to 0. If it is equal to 0, then either b is 0 or L is 0. But we already assume that b is greater than 0 and L, it is a length of this tree, so it is never be 0. So that's why this quantity is never 0. So that's why a is 0. Since a is 0, we can have b is also 0. So that means in this case your y, function y, is also 0. So that means we achieve for lambda is greater than 0, we get a 0 solution. And we are not looking for 0 solution, we are looking for non-zero solution. So this will gives me, therefore a is equal to 0 and b equal to 0, which implies that your x of x is 0. I can say that hence there is no eigenvalue, lambda is greater than 0. So that means this solution is not possible. Case number 2. Case number 2 will consider the lambda is equal to 0. Here x double dash minus lambda x is equal to 0. This is the ordinary differential equation with these two conditions we have. Objective is to solve this one. But lambda is 0, so that's why this will gives me x double dash is equal to 0. That will gives me x dash is equal to, if I use the method of separation of variable, that will gives me x dash is constant. And this will gives me x is equal to ax plus b, where a and b are constant, arbitrary constant. If I use this condition, x of 0 is equal to 0 and x of L is equal to 0, we have, that is x of 0 is 0, which gives me, if I can use that, that means x is 0, so we'll have b is 0, and x of L is equal to 0 will imply that AL plus b is 0, but b is already 0, so that's why AL is 0. But L is the length of the strings, which is never 0, so that will imply A is 0. Here also we have x of x is 0 for all x between 0 to L. So therefore we can say that lambda is equal to 0 is not an eigenvalue for this problem. Now the last case is left where lambda is negative. Case number 3, lambda is the negative. If the lambda is equal to negative, then we have, let us consider b equal to minus, lambda equal to minus b square for b belongs to. This we have given eigenvalue problem is x double dash minus lambda x is equal to 0 with the two conditions, that is x of 0 is 0 and x of L is 0. We'll have it is x double dash minus plus b square x is equal to 0. Therefore, here the auxiliary equation is m square plus b square is equal to 0. Minus square is equal to minus b square, and that will give me m is equal to plus or minus ib. That means there are complex roots is there, and if you have a complex root, right, alpha plus or minus I beta, then we have a solution is e power alpha x cos beta x plus a into cos beta x plus b into sin beta x. So this will be the solutions we have if the roots of the auxiliary equations of it is alpha plus or minus I beta form. So therefore, solution of the given problem is x of x is equal to, we just observe that here alpha is 0, that means e power 0x, in bracket it is a into cos beta x, beta is b x plus or minus b into sine beta x. Beta here it is b. Finally, we'll have a into cos bx plus b into sine bx. This is x of x we have. Now, using this boundary conditions, I use that x of 0 is equal to 0 will implies that if I substitute x is equal to 0 here, we know that sine 0 is 0, so we'll have a is 0 because a into cos 0 is 1, and x of L is equal to 0 implies that a into cos KL plus b into sine KL to 0, but a is already 0, so that will imply b into sine KL is 0. If b is also 0, then we have a 0 solution again. B never be 0 because we are looking for non-zero solution. So in this we can say that sine BL is 0, because if b is 0 then u is 0. That means our solution is 0. We are not looking for 0 solution. And if sine b is 0, that means that the BL it is pi. Sine is 0 for 0, pi, 2 pi, minus pi and so on, where n is running from 1, 2, 3 up to so on. That means the value of b, that is the lambda we got, it is n pi by L. Therefore, the value of b is n pi by L, where the value of n, I can say it is 1, 2, 3 up to so on. Here we need to find out what will be the value of lambda. So therefore b square will be n pi by L square, and we know that the value of lambda is minus b square, so that way this b square is minus lambda, so the value of minus lambda is n pi by L whole square. This lambda is actually depends on n, so that's why I am just saying it is lambda n, and n running from 1, 2, 3 up to so on. So I can say that this lambda n is the eigenvalue. This lambda n are called eigenvalues. And what are the eigenfunctions? That is our value of lambda x, the solution, that is x of x. We know that this x of x is cos bx plus b sin bx, but value of a is 0 and the value of b we got from this, that is n pi L, so that we can have it as b n pi x upon L. And since we have considered your lambda, this value depends on n, I just say that this is also depends on n, and this is bn, which is a constant, which is also depends on n. So this is actually is the corresponding eigenfunction for the eigenvalue problem. Now we need to find out what will be the Tn, what will be the T solution. The other equation that we have obtained it into this, so still now we have just solved the one side thing, that means we have solved this solution of this problem. Now we have this one, but here the value of lambda is negative, that means it is minus b square. So now we'll solve that portion. We have t double dash minus t c square lambda t equal to 0. The value of lambda is minus b square, so that's why it is t double dash minus c square b square, and this minus become plus t equal to 0. So the auxiliary equation for this one, the auxiliary equation, this equation is square plus c square b square is equal to 0. Therefore it will give me m minus I c. Also we have a complex roots. So as we have did for x, the solution t of t is equal to power 0t, because alpha is 0 here. Already used the value of constant a is previously, so it will say it is a and b is used, so it is c cos c bt plus b into sine cbt. This e power 0 is 1, so this will we can write down c into cos c dt plus d into sine cbt. Since this value of b it is depends on n, value of t is also depends on n. So for that I'll just write down putting the value of beta here. This value depends on t, so we'll have Tn, t is equal to Cn cos n pi Ct by L plus Dn sin n pi Ct by L, where this Tn is dependent, n is running from 1 to infinity, and Cn and Dn are arbitrary constants. Therefore, finally we have the solution. Hence, the solution of the given problem, that is yn of t xt, because we have y of xt is equal to x of xt into p of t. We already obtained the value of x of xt and t and t. So that's why we can have this depends on n, the solution is depends on n, and the solution will be, that means equal to Bn n pi x upon L, that is the value of xn we have obtained it, and the value of Tn is this Cn cos n pi Ct by L plus Dn sin n pi Ct by L. And we'll just observe that if I multiply this Bn with Cn, we'll call it as another variable. Let's say it is a small an, and this Bn is multiplied with this Dn, we'll call it as Dn. They are also arbitrary constants. So finally what we have, it is equal to yn of xt is equal to sin n by x upon L, in bracket it is an cos n pi Ct upon L plus Bn sin n pi Ct upon L. Solution, equation 1. We have a solution of the wave equation. And as we have discussed in the starting of the video, that if we have a y1 and y2 are the two solutions of linear homogeneous boundary conditions, then y1 plus y2 is also solutions of the same equation, which is linear in the same boundary conditions. We already observed that equation 1 and the boundary conditions are satisfied and they are linear and they are homogeneous into that. So therefore, by principle of superposition, is f xt is equal to summation n running from 1 to infinity yn of xt is convergent, also solution by equation 1. That means the given wave equation, this will also satisfy and satisfying boundary conditions. In fact, we also assume that term by term differences is also possible and derive the convergence. Here we have the solution, it is y of xt is equal to summation n running from 1 to infinity sin n pi x upon L an cos n pi Ct upon L plus Bn sin n pi Ct upon L. So this will be the solution we have. Now here there are unknowns, that is an and bn, and still we have not used the initial conditions. This solution should satisfy the initial condition. So the initially we have given y of x 0, that is at time t equal to 0, the displacement is f of x. It gives y of x 0, that means if I substitute t equal to 0 here, the sign 0 is 0. So that's why this term will tend to 0. You have t equal to 0 here. This value, that means the value of sine will gives me 0, and this value will gives me 1, because cos of 0 is 1 and sine of 0 is 0. So this value is not appearing, only here the left quantity is an. So that's why we can have this summation n running from 1 to infinity an sin n pi x upon L. And this side it is actually f of x. It is look like a Fourier series, half range Fourier series. To calculate given by Fourier series, Fourier equation, half range series, sine series of f of x. An is equal to 2 by L integration from 0 to L f of x sine n pi x upon L dx. Similarly, if I can use the another initial condition, that means similarly initial condition y of t x of 0 is equal to g of x for all values in between 0 to L. This is the initially is there. So that means we need to differentiate first with respect to t. So that's why we can have differentiating by respect to t, get t of x t is equal to summation n running from 1 to infinity sine n pi x upon L, which is independent of t, so that's why it stays as it is, an. Then we have a cos n pi ct upon L. So the derivative of cos is sine, so that's why it is sine n pi ct upon L into, you should have a multiplication is n pi ct upon L bn sine, so that's why here it is minus. Then it is bn, the derivative of sine we have, it is a cos, so it is n pi ct upon L, and this derivative of this n pi ct upon L is n pi c upon L. Substitute t equal to 0 here. In this case, this quantity will become 0 and this quantity will become 1, because sine 0 is 0, cos 0 is 1. So this will gives me summation n running from 1 to infinity n pi ct upon L bn into sine n pi x upon L. This is equal to g of x. This is also a half range Fourier series. So if you want to calculate this bn, which also can be calculated using the half range sine series. Series, the half range bn equal to 2 by n pi c integration 0 to L g of x sine n pi x upon L dx. This constant is appear due to this situation, that is we have already multiplication with the bn is n pi c upon L. It is already in the multiplication of bn is there, so that's why this quantity is appear here, and we have achieved the same result when we are deriving the D'Alembert using the D'Alembert solution for finite string. We can conclude that if you have a given a vibration of a string of a finite length or a wave equation of a finite length, it is given with the initial condition, that means the displacement is given f of x and the velocity, initial velocity is given as g of x, and these two boundary conditions are given, then you can write down the solution which is in this form, that is y of xt is equal to n pi x upon L, where L is the length of the string, an cos n pi ct upon L plus bn sin n pi ct upon L, where this an and bn can be calculated using the half range coefficient of half range Fourier sine series. That's it for this video. If you like this video, please press the like button. If you have any comment, suggestion or question, please drop down in the comment box below. See you in the next video. Till then, bye bye, sayonara.